In this video, we are going to get a sense of why the linear regression equation gives us the line that best fits all the points in the data compared to another line. It's not a complete proof, but to give you a sense. Now, the linear regression equation, if you compute residual as observed y-score minus predicted y-score for the same value of x, take all those residuals from all the points and square them, add all of those up, then you're supposed to have the sum be the least that it could be. That's what you get from the linear regression equation. Let's take a look at an example. Here we go. Now, we are asked to draw the scatter diagram for this set of 5 ordered pairs. First of all, we were asked to do this by hand, although StatCrunch is an option where we could bring that up. We have 10 spaces along the bottom in choice A, which would mean those are going by 3s. That first point we're seeing, the lowest x value in that table of data is 4, but since they're going by 3s here, that first point towards the bottom left would have an x coordinate of 9. And here, the spacing is by 1s. So that point would have an x coordinate of 1. That can't be right. The next two choices also have spacing by 1s. So it is possible that in terms of looking at that first point and the x's, looks like we have an x coordinate of 4 here and an x coordinate of 4 here as well. But we're supposed to have 4, 9. The y-axis is only going by 1s. On choice D, that would mean that that point is 4, 4. Here we're going from 0 to 30 with 10 spaces, so the spacing has to be by 3s. It would make sense that we are looking at 4, 9 there. We are asked to write the equation containing the first point in the table and the last point, 4, 9 and 9, 24. To do that, I'm going to compute the slope and then plug that in along with one of the points to find out what the y-coordinate of the y-intercept is. So our 2 points were 4, 9 and 9, 24. There, that should be better. Let's call this our first point. So x1 sub y1 and x2 sub y2. Our formula for slope, y2 minus y1, all that over x2 minus x1. Got 24 minus 9 in the numerator. Since I started with 24, I've got to start with a 9 in the denominator and subtract the other x coordinate. So that's giving me 15 over 5. My slope is 3. Put it in slope-intercept form. I know the slope is 3. So if I could just solve for b, I could take either one of these points. If I do my work correctly, I can solve for b. So I'm going to take the first point. X is 4. And y is 9 is paired up with that. Clean up the arithmetic here. Subtract 12 from both sides. And we have that b is negative 3. Now, I'm not going to write plus negative 3, not on paper or on a board. I would write that as 3x minus 3. However, let's see what options we were given on my lab. They had that as a plus sign, so I don't have a choice. 3x, they already have the x there. So just type the slope in front of the x, and then The y-coordinate of the y-intercept is -3. That point, that equation, should go through the 0.49 and the 0.924. Looking again at the labeling here, the one that worked back up here had the x's going from 0 to 10 and the y's going from 0 to 30. So I'm hoping it's either choice A or choice D, but taking a closer look here. So going from 0 to 10 here, we're looking at spacing by ones, and 0 to 30 here, 10 spaces, so spacing by 3. Looks like that is 4, 9, and then 924, and the line is going through that. I believe it is choice A at a quick glance. Now it says by hand. Let's just go ahead and let StatCrunch do that for us. Find out the equation of the regression line, and we would go to stat, regression, simple linear. They've already labeled where the x and y variables are. Compute. And for that first part, we could have just pressed that right arrow to see the scatter plot. We're also seeing the regression equation lines graph. But for the equation, they want rounding to 3 places. So look at what's in front of the x. I figured that this equation should be pretty close to the equation we just came up with. What's in front of x is a 2.977, which is pretty close to the 3 we just found for slope back here. And then that value is the constant, so that's the y-coordinate of the y-intercept. Graphing that, we just saw that here. And what we see is that second point's a little bit below. The third is a little bit above it, a bit more than the previous. And the fourth point's a little bit below. So let's see. Perhaps it is choice A. Find the sum of the squared residuals for the line found in part B, where our formula was the y equals 3x minus 3. So I'm going to download this to Excel. What I'm about to show could also be done in StatCrunch, although I've only done something like this once. And it could also be done on a TI-84. Let's find out our predicted y values with that formula, y equals 3x minus 3. Residual is the observed value from the data minus the predicted value. That 0 means that the line y equals 3x minus 3 went through that point. It also went through the last point. There's only one point that it missed. We want to have the lowest possible sum of all the residuals squared. Now, this should be kind of easy to see for this example, that 4 of them are going to be zeros, and 1 of them will be a 1, and then the sum of those 5 residuals squared is just going to be 1. So the sum of the residuals squared is 1. No rounding needed. And then we are going to repeat that with the least squares regression line found in part D. I am uncertain if they want us to use the rounded values that we have here. So I'm going to start off playing it safe by copying this over. Put that in Excel. So now the way we are predicting is use that formula with the X values over here. Build that in for the rest of the points. And changes I made then got changed for the residuals. And they're squares. And they wanted that rounded to the 3 places. So the 6 in the 4th place should round that up to 0.791. Let's see if that will be accepted. If not, then I'll use the rounded coefficients that we entered back here in part D. So the line in part B passed through 4 of the 5 points, but the line in part D has the smallest sum of the squared residuals. We haven't considered all possible lines, but again, this is not a proof, but to give you a sense that we are actually getting a better, in fact, the best fitting line from the linear regression equation. Okay,